Hi all, welcome back to another round of physics. And today we're going to discuss a particular type of circuit element called an inductor. Inductor. And just like a capacitor, which stores energy in the electric field, we are now at a point where we can discuss how to store energy in the magnetic field, in B field. And we'll use Faraday's law to get an idea about what the equation is for an inductor. Just like how we used Gauss's law for the electric field to analyze a capacitor in order to get the energy storage in the electric field. And in this case, you remember we found that E, the magnitude of the electric field, was equal to sigma over epsilon naught, which meant that the difference in potential between the two plates was something like Q over A. That's just re-expressing sigma. We still have the epsilon naught, and then we multiply by the plate separation. Okay. And then we lumped the physical characteristics of the parallel plate capacitor into a term which we called the capacitance. We said Q over C, where C is defined as A epsilon naught over D. Okay, so we're going to do the same thing using Faraday's law to analyze a circuit element and figure out how to store the magnetic field. And the circuit element that we need to consider is a coil of wire, what I would refer to as a solenoid. So you have a solenoid, a repeating coil of wire through which current is going to run. And you can imagine, you make this long or as short as you want, I guess. Let's make it long enough. We need to make it long enough so that the magnetic field inside is fairly constant. And I want you to consider two loops. Well, actually, let's analyze it first from a qualitative standpoint, and then we'll go through and get the quantitative. So imagine for a second you have a solenoid, and I'm going to identify two loops. I'm going to identify a loop at the bottom of the solenoid, and I'll identify a loop at the top. Okay. Now, you know that those are slightly not connected. You know that one loop goes to the next loop, goes to the next loop. We're going to model it as if it were two separate loops for a moment. Now, here's the question. Let's go ahead and draw in some axes real fast. And just to keep our mind flexible, I'll call this one the X, I'll call that Y, and I'll call this Z. Now let's say for a moment that I start running current in the solenoid. I start putting current in this way. Okay. First question I have for you. Due to this circulating current, so let's model this as a complete wire for a second. Due to this current in this top loop, okay, what's the magnetic field direction at the location of the bottom loop? And I'll put an X there. Go ahead. Take a minute, see if you can come up with the answer. You got it? You're not supposed to get it that fast. I mean, like, don't, pause the video, right? Okay, so let's get an idea. We can use our right-hand rule shortcut, if we want, to figure out what the direction would be. We know that, okay, right-hand rule shortcut would be grab the wire with your thumb pointing in the direction of current. So I'm pretending to grab the front part of that coil, and the current should be going to my right. So the magnetic field generated by this loop, okay, should be going up through the center of the loop and then looping around. So in other words, the magnetic field should look something like this. Okay. And I'll try that back one as well. Go behind the wire, and then here it should be going like this. So up through the center, and then down on the outsides. Okay. So way down here, the magnetic field will be, and we don't have to get this perfect, but we just need a general idea. Down here, right below the central axis of the top loop, the magnetic field should be pointing up. And I'll call that B external for a moment. So as I start running current in the top coil, I now have an external magnetic field pointing up through the bottom coil. Now we're going to leave this qualitative. I'm not asking you to actually get me numbers yet. Okay. But let's compare this. Compare now the situation to before the current started running to after. What can you tell me about the change in magnetic flux in the bottom coil? It's increased. The change in flux has gone up, right? The area stayed the same, the angle hasn't shifted, but the magnetic field strength has increased. So the flux through that bottom coil must have gone up. So you probably know what the next question is that since the flux has gone up, okay, what direction will an induced current run in the bottom loop? So we're trying to figure out that negative sign right now, right? So if the flux has increased, this bottom loop will want to run a current to oppose that increased flux. Okay, well that means that I need an induced magnetic field, and I'll use a darker green, I guess. I need an induced magnetic field to be going downwards through that loop. And if I want that field to be going downwards, I can then use my right-hand rule shortcut. I need it going, again, front of the loop. I need it to be going downwards into the loop. That means that my induced current has to be running to the left. It has to be running this way. Again, we're just applying that Lenz's law, that negative sign that we see in Faraday's equation. And I'll write down the rest of this here just for completeness. In other words, okay, we have the induced current in response to the initial current being run in the top loop. Incidentally, I'll hint at something here as well. Notice this is also the basis, and we'll come back to it, to something like inductance charging. Right? You run current in one loop, and current starts running in a separate second loop that's not even touching. That's how a lot of toothbrushes and I think the AirPods and, not an electrical contact, but a magnetic connection. Okay, to be continued. Now, the cool thing, we notice that the induced current runs in a direction opposite of the initial current. So now we have our mechanism for storing energy in the magnetic field. Let us now return back not to the single loop case, but the solenoid case. So I'll go ahead, let's write down Faraday's law again. Just to remind ourselves. Okay. So I'll try to draw this solenoid a little bit more precisely than I usually do. And try not to erase it. Now imagine that these loops are packed tight enough together, okay, so that you can approximate each turn as an individual loop. And we have now had an idea about, well, one loop can generate a magnetic field at the location of a different loop. And in response, that bottom loop runs a current that opposes the current in the top loop. So now I'm just connecting them all together. And let us, for a moment, consider, say, this bottom loop. In other words, what do I want to consider? I have a single loop at the bottom and an entire solenoid. I won't draw the individual coils, but imagine that I now have an entire solenoid. That would have been a better way of drawing it, actually. Now here's the question. And due to this entire solenoid, first of all, we should ask ourselves, what's the magnetic field due to a solenoid? And if you don't remember it, I don't remember it either. Okay? Usually I have to, in my head, think about how to rederive it. And this is one that you'll probably want to have locked in your memory banks at some point. Just like the parallel plate capacitor, the electric field between plates of a parallel plate capacitor, this is the other one that's nice to remember how to derive and have that locked into your memory banks. Okay. So this one is given by, and we could apply Ampere's law to get it. I won't review that. There's another video for that. This one's given by mu naught N I, the current running through the solenoid, divided by the length of the solenoid. Okay. So I'm going to leave it in terms of N and L rather than the turn density. Okay? So we have the magnetic field strength of the solenoid. And again, I'm going to ignore the fringe field. I'm ignoring that idea. And then we can ask the same question. If I start running current, excuse me, that's the opposite direction than we had in the first example, isn't it? So now we have the same idea. If I start running current in this solenoid, and I'll run it to the right on that front face, this bottom loop will see an increase in the magnetic field and run a current in the opposite direction due to that field. Let's go ahead now and find quantitatively what that value is. Okay. So we apply Faraday's law, and we've already determined via Faraday's law that the current should be in the opposite direction, okay, opposing the current in the solenoid. So we'll write, we have Faraday's law. We'll say that the area of this loop is A, and so the flux through the bottom loop is given by A mu naught Ni over L. Right. The area of the loop times the strength of the magnetic field passing through the loop. And because it's a solenoid, remember, one of the nice features of a solenoid, just like a parallel plate capacitor, is that the magnetic field through the solenoid is constant. Right? I mean, you can see that from writing down the equation, but I just highlight that it's constant. So if it were non-constant, then we would have to go back to the formal definition of flux. And we would have to do the integration. Right? We'd have to actually do that integration if the magnetic field strength varied at every point along the area element of the bottom loop. So we have the flux that is the bottom loop. Now let's ask another question here. Okay, so this is part of the way through. Let's keep going. Excuse me. Next question, of course, is okay. Well, we want to apply Faraday's law. We have the changing flux per time, and we'll have to look at this and say, okay, well, for a solenoid, for this situation, solenoid in a single loop, which of these quantities is actually able to vary in time? Well, we have a fixed area, constant number of loops, constant L. All of these are constant. These are physical properties of space or the arrangement of the loops. So the only thing that can change is this current flowing through the solenoid. So we better put in a mu naught N over L. We'll put di dt. Now, one way you could argue this di dt, is that you start putting a current I in here. Okay? And because of that current I, there is an induced current in the bottom coil. We already talked about that. But now we could go a step further. Because there's an induced current in the bottom coil, that means that that induced current generates an induced magnetic field, and that induced magnetic field has a flux through the original solenoid. Well, because of that changing flux through the original solenoid, there is a new induced current, which I'll call induced 2, which generates its own induced magnetic field 2, which then has a flux, then generates an induced current 3 through the bottom, and you kind of see it. It keeps going back and forth. Okay. So that's how you could think of the current through the solenoid actually changing, is that in response to the induced current, there's another induced current in the solenoid, which induces another current in the bottom loop, and it kind of backs and forth. The upshot is that each time you kind of run through that process, the induced current gets smaller. So there's some asymptotic behavior that you'll eventually reach. And we'll see what that behavior is when we apply Kirchhoff's laws. Okay. Well, I've just looking at the magnitude right now. So I'm going to drop the negative sign. And applying Faraday's law, we then have a situation where we can write, I'll just rearrange these variables here, over L di dt equals, and I've been using EMF, but I told you that historically this is the same thing as delta V. Okay, so I'll write it as delta V here. Now, here's the last piece, and then we're home free. Okay. Is there anything special about the bottom loop of the solenoid? No. Right? I chose the bottom loop just for conceptual purposes, but imagine for a moment, how would this process change if you chose, say, the loop in the middle of the solenoid? Let's say we choose that one. Well, conceptually, I guess what would happen? Conceptually, what would happen is we would have a smaller solenoid on top of that loop. We'd have a smaller solenoid below the loop. Okay, so again, my terrible pictures. You'd have a solenoid here. If we say it's midway, we'll call it L over 2. You have a second solenoid of L over 2. And then you have this loop right in the middle that you're dealing with. Say L over 2 and N over 2. We have a second solenoid, N over 2 and L over 2. Okay. But the question is would my approach actually change? No, it wouldn't, right? We would still get the same magnetic field strength going through the solenoids. or excuse me, yeah, we get the same magnetic field strength, okay, and the same magnetic field flux going through this center one, this one right here. And in fact, we could do that you could do the top loop or the midway point, or, like you could do this process, the flux through each of the loops in the solenoid. Okay. So it doesn't matter where that loop is located. So the next question, what happens if I want the total magnetic flux through not a single loop in the solenoid, but every single loop in the solenoid due to the other loops? You got it? Good. If this represents the potential drop across one loop in the solenoid, then this must represent the potential drop. Okay, so I'll call this one loop. I'll label this loop. Then this expression must represent the potential drop across the solenoid. One change. Right? If I take the single case and multiply by the number of loops in my solenoid, I should get the case for the entire solenoid. So boom, there we have it. We now have an expression that tells us the potential drop across a solenoid when we start running current through it. I'll rewrite it here. Oh, you should yell at me. Excuse me, I forgot the most important part. di dt. Couple things to note. Number one, notice that out in front, this term of this grouping of constants depends only on the physical characteristics of your solenoid. Where have I heard that before? Yeah, remember the capacitance only involves the physical dimensions of your parallel plates. So right here, this portion that I've bracketed off, that is sometimes referred to as the inductance. Okay. So we'll define that. The inductance is this mu naught A n squared over L. I should say, excuse me, I'll put equals. Right. This is the expression for a parallel plate. This is the expression for a solenoid, which is the, if I may say, that's the canonical example, but you could come up with other ways of doing this. So in general, an inductor, the potential drop across an inductor is given by this expression, delta VL, call it capital L, excuse me. Similar to, this is the capacitance for a parallel plate capacitor, but in general, the potential drop across a capacitor is given by Q over C, is give the potential drop across a capacitor. Pretty cool, huh? And of course, for completeness, we have the potential drop across the resistor. Ohm's law. I don't know why the capacitor and the inductor equations don't get their own name. Not quite sure why that is. Life goes on. And oh yes, we might as well. The resistance also depends on the physical characteristics. Remember, you have resistance is equal to the resistivity times the length divided by the cross-sectional area. So again, resistance, capacitance, and inductance generally deal with the physical dimensions of the object you're using. Cool. We'll point out a couple of other things. For example, when we are dealing with an RC circuit, so say we have an uncharged capacitor and we hook it up with a battery. We conceptually thought of additional charge being dumped onto one plate of the capacitor and pushing charge off of the other plate so that one side becomes high, positive charges, and the other side becomes low, negative charges. Or maybe I should say absence of positive charges. And this process continues until the drop across the capacitor was equal to the potential of the battery. So there's some sort of limiting behavior. And we went through and actually solved Kirchhoff's voltage laws, time and V. Capacitor, I'll put V cap here. If we've gone through and solved Kirchhoff's voltage laws to see that you will get some sort of asymptotic behavior that looks like, let's see, it must be 1 minus e to the negative t over RC. Something like this. I'll put V back here. Right, at time equals 0, there is no charge on the capacitor. And as we increase, we get full charge. That means the drop is equal to the drop on the battery. For the case of an inductor, okay, we can already imagine what would happen. Let's say that we put a resistor, and now an inductor is represented by loopy wire. So instead of the sharp edges, you have to loop them. Almost like the symbol for a light bulb, I guess, but multiple. So remind me, if I start getting sloppy too, remind me, but sharp edges, sawtooth, that is a resistor, and loopy is an inductor, circuit symbols. And already we can kind of get an idea about what's going to happen. Okay? Say for a moment I have an uncharged inductor in my circuit. I close the switch, and so I go from having no current, zero current, to having a large current, say I. Okay? So a very slow or fast change. Fast. I throw the switch, boom, the current jumps up to I. Okay. Now, because I have a large change, what can you tell me about the potential drop across the inductor if I have a very rapid change in the current? The potential drop across the inductor is also going to be large. If I throw the switch and the current suddenly jumps, the potential drop across the inductor is going to be large. And so the total current through the circuit is going to be low. Okay. What happens? Well, I throw some current I, start running, And because of the loops of wire, those loops suddenly see a huge flux of the magnetic field. And so it will produce an induced current induced in the circuit. And at that brief instant when the switch is closed, the induced current is going to be equal to the original current you're trying to drive through the circuit. In other words, it's almost as if there were no current running at all, just for that brief second. Now, as, excuse me, say in the first time step, I go from 0 to a current I. Okay? But in the next time step, say 1t, now I'm going from I to I. Okay? So as the next time step, I'm not changing as dramatically. I'm very generalized. We could see this in the equations once we get there. Okay? But in the next time step, I'm not changing very much, which means after a moment in time, the induced current, right, I'm not changing I very much for the second time step. That means that my change in I per time step is smaller, which means that my induced current's going to be smaller. And as time progresses, this induced current will get smaller and smaller and smaller until the induced current is 0. What do I want to say about this? At short time intervals, close to 0, the inductor acts like a break in the circuit. It doesn't want to allow any current to flow. But as time progresses, that inductor resembles more and more like a perfect wire, until after everything is settled down, this inductor plays no role whatsoever. If the current is constant, it doesn't change in time, and so the potential drop across the inductor is 0. So at long time intervals, the inductor looks like a perfect wire. Notice that's exactly opposite of what an uncharged capacitor does. An uncharged capacitor at time equals 0 has no charge, and therefore there is no potential drop across the capacitor. But at long time intervals, when more charge has accumulated on the plate of the capacitor, it looks more and more like a break, or I should say the potential drop across the capacitor increases to the point where the potential drop equals the drop across the battery. And the capacitor starts looking like a break in the wire. Current stops flowing altogether. Cool, right? You have a circuit element that acts like a perfect wire at the beginning and a break at the end. That would be a capacitor. You have a second circuit element that looks like a break at the beginning, doesn't let any current flow, and after long periods of time looks like a pure wire, perfect wire, excuse me. Nifty, right? Okay, I'm going to stop here for right now just to have a shorter video for the inductor introduction. And then we'll run some an LR circuit or an RC circuit. We'll start thinking about how do these inductors work in circuits themselves. So stay tuned for that video. I'll get this one posted and I'll see you soon. Thanks for your attention.